In this video, we review the foundations of adiabatic bomb calorimetry, and we utilize an applied example to see how it works. Alright, adiabatic bomb calorimetry is an experimental technique to determine the enthalpy of reactions. And the enthalpy of reactions is the bread and butter of thermodynamics or the first law in chemistry and the life sciences, because that's the type of metric that you can use to determine whether you need to supply some energy for a reaction to proceed, or whether you can use the reaction or the energy generated in a reaction to power something else, right? So knowing that value of the enthalpy of the reaction is quite kind of important. So what we'll look at here is an experimental technique to be able to do that reliably. Okay, so here what we have is your bomb calorimeter, and bomb here means constant volume, right? That's going to be a keyword in the technique. The technique is at constant volume, which is useful. Right, so the idea is that you're going to be putting some fuel, something that you want to burn, into this bomb calorimetry, and what that means is that the bomb calorimeter is very good to determine the enthalpies of combustion reactions. And combustion reactions are extremely important because our body is fully powered by the combustion of carbohydrate, glucose, and fat, and a little bit of protein, right? All those are combustions, right? So knowing what the enthalpies of those reactions are, perhaps by using bomb calorimetry will be very useful. And to some extent, you know, the way that we power our world is still through fossil fuel combustion, right? So the same thing could actually be done here. You could put there maybe coal or natural gas or any other fossil fuel and determine what is the enthalpy of combustion that you utilize when you burn that gasoline in a car or burn that coal in a power station. All right, so again, this is the fuel, and it could be a solid, a liquid, or a gas, and you have an inlet to burn it with oxygen, and that is a hallmark of a combustion. You must use oxygen gas as a reagent. And then to start the reaction, you have here some ignition mechanism that simply just starts the reaction. And the idea is that these combustion reactions will be exothermic. So the energy will be released as heat to the surroundings, which should get hotter. Right, so to then capture all that energy released as heat, what you do is you just put this bomb, this constant volume device, into a bath of water. Okay, so this will be a metal casing with some water in it. That's what we call the calorimeter, right? So all of the energy released by the reaction will be absorbed by the metal casing and the water of that calorimeter, which will get hotter, right? And then you can determine what the temperature change is in that calorimeter. And if you know what the heat capacity of the calorimeter is, then you can determine how much energy as heat has been transferred from the reaction to the calorimeter. And then if you know what the energy transfer as heat in the reaction is, then you can determine both the change in internal energy and enthalpy. Right, so to illustrate how that works, we're actually going to run an applied example. So this video will be a little longer than usual, but it will show you fully how to solve a problem in bomb calorimetry. Okay, so the fuel that we're going to be using is benzoic acid, which is this molecule, and has stoichiometry. So this is benzoic acid, which you can write simply as C6H5COOH, which is a solid. Right, that is your benzoic acid, and we're going to have an amount of 0.4088 grams of this molecule that we're going to put in this sample holder, and then we're going to burn it with oxygen to determine what is the enthalpy of combustion of that fuel. Okay, great. So the first thing to do is actually balance what the combustion reaction is, right? So we know that the second reagent, aside from the fuel, is going to be your oxidizer, which in combustion is O2 as a gas. And then the products are always going to be CO2, which under normal pressure and temperature conditions will be a gas, CO2. And then water, and importantly here, you have to recognize that we normally run these experiments at a temperature close to room temperature, so that will be 25 Celsius and so forth, or close to, right? And then the pressures are very close to 1 atmosphere of pressure, so the stable phase of water under those conditions happens to be the liquid, right? So in all of the combustions that we're going to go running, water is not a gas. Is simply a liquid, and that happens also inside your body. Benzoic acid, if you eat enough of it, will kill you, but if your cells could actually digest it and metabolize that, the products of that metabolism would be CO2 gas and water liquid, which is what you get from when you burn glucose in your cells. Okay, so now that we understand what the products are, and this will be the case for any fuel. If you have here methane, methanol, coal, anything that you want, you're always going to get CO2 gas and water liquid. Of course, if the molecule has other atoms like nitrogen or sulfur, then there will be other products. But for hydrocarbons, carbohydrates, and molecules that only have C, H, and O atoms, the products will always be CO2 gas and water liquid. Okay, so so we just have to balance these, right? So when we think about the reaction, notice that you have here 7 carbon atoms. That means that you need a 7 there, and then hydrogens you have 6. That means that you need a 3 there, and then you close this by balancing the molecular oxygen. So notice that you have 3 and 14. That is 17 oxygens, but you have 2 there, so that is 15. Which means that you're going to have here a 15 halves oxygen. It is important to balance these reactions with a stoichiometric coefficient of 1 for the fuel, because you're interested in the enthalpy of burning 1 mole of fuel, right? So what that means is that it's okay to have fractional coefficients in the rest of the substances as long as you have a stoichiometric coefficient of 1 for that fuel. All right, so now we need some additional data for this problem, and the data is that when you burn this amount of that fuel, the temperature of the calorimeter, right, so the bath of water and the metal casing, increases from an initial temperature of 25,000 Celsius to a final temperature of 27.050 Celsius. And notice that here the difference in temperature, which is what we really care about, the difference in temperature in the calorimeter, so I'm going to write here subcal, right, that is simply 2.050 Celsius, and it will be exactly the same change in temperature in Kelvin, because the Celsius and Kelvin scales are simply offset, so differences in both of them are equivalent. The last piece of information is this, that the heat capacity of the calorimeter is also known, and this value is 5267.8 joules per Kelvin. All right, so you need to supply more than 5,000 joules to elevate the temperature of the bath of water and the metal casing, which we call the calorimeter, by just 1 degree Kelvin. Okay, so from this data, our goal is to calculate what the reaction enthalpy is for this combustion. Right, that's what we're trying to do here. Okay, great. So, all right. So the first thing that we do is to determine what is the amount of energy as heat absorbed by the calorimeter as a consequence of the reaction taking place. Again, so you're burning this, that generates energy as heat, and all that energy gets dumped into the calorimeter. Okay, but notice that the only thing that is taking place here in the calorimeter is a change in temperature. So we can actually calculate the heat in the calorimeter very simply as this. The heat in the calorimeter, this heat capacity is constant. It will be the integral of the heat capacity and then differential of T. But because this heat capacity is constant, it does not depend on temperature, this is simply the heat capacity in the calorimeter multiplied by the change in temperature in the calorimeter. Okay? That's all that you have right here. Right, so we actually have this number. This is the heat capacity of the calorimeter, that is this number. And we also have the change in temperature in the calorimeter, is that number. So the product of those two is going to give you the amount of energy as heat absorbed by the calorimeter, which happens to be a number of 10.80 kilojoules. Right? That is the heat capacity, the heat absorbed by the calorimeter. Okay, great. So here comes a key step, or one of the key steps in bomb calorimetry. Right? The idea is that the calorimeter completely surrounds or engulfs the system. Right? So every single joule of energy released by the reaction is going to end up in the calorimeter. Okay, so that's actually what adiabatic here means. That means that no energy is lost anywhere else. Every single joule generated in the reaction ends up in the calorimeter. Okay, that's the adiabaticity here. So what that means in terms of an equation is that the heat released by the reaction is going to be exactly the same as the heat absorbed by the calorimeter, but with a difference in sign, right? Because the calorimeter absorbs energy as heat, but the reaction releases energy as heat, right? So you need to change the sign there. And what that means is that the heat released by the reaction is simply minus 10.80 kilojoules, right? So it's this is a beautiful concept here, because notice how simple it is to just measuring things in the surroundings in the calorimeter allows you to determine what happens in the system, which is what you're interested in. Okay, so great, that's a good step, right? And now we can erase everything that has to do with the calorimeter, because we've already handled it, right? So we actually only have to think about the reaction now. Okay, so the question is, how do we go from this heat to the enthalpy, right? Well, the first thing to recognize is that this process, the reaction, is taking place at constant volume, right? So this key of the reaction is really Q sub V, and we know that Q sub V, constant volume, is equal to the change in internal energy. Okay, that is one of the conclusions, or one of the things that we learned in the first law. Okay, so what we have is that automatically we know what delta RU is, and that is simply minus 10.80 kilojoules. Okay, great. So we know the change in internal energy in the reaction. Now we actually have to go to calculate the change in enthalpy for the reaction, because that's what we really want to know here. Now, notice that what we're really after is actually the change in energy or enthalpy per mole. Okay, but the number that we have calculated until now is simply the change in internal energy in the combustion reaction, but for this amount of benzoic acid, right? So again, notice that if you actually burn twice this amount of benzoic acid, the change in internal energy would be twice this number. Okay, so to avoid this confusion, what we actually do now is calculate the change in internal energy per mole, and that just removes any dependence on how much initial sample you had. Okay, so let's try to do that. Remember that to go from the internal energy to the internal energy per mole, the only thing that you have to do is just take the change in internal energy of the reaction and divide it over the number of moles. And that is easy to calculate because we have the mass, and we know what the molar mass of benzoic acid is. We actually have this stoichiometry, right? So this is simply going to be minus 10.80 kilojoules divided over moles, which is mass divided over molar mass. So that would be the mass 0.4088 grams divided by the molar mass of benzoic acid, which is 122.12 grams per mole. And this is going to give you the reaction enthalpy, sorry, not enthalpy, internal energy per mole. Okay, so this is minus 32.26 kilojoules per mole. Okay, and there's just one more step that we need to work out to determine what the change in enthalpy is in the reaction. Okay, so we actually have now the change in internal energy. Now we got to go and calculate the change in enthalpy. But of course we can do this with the definition of enthalpy. Remember that enthalpy, or change in enthalpy, was simply change in internal energy plus delta PV. But of course we're always neglecting components that are not gases. So the way that we usually treat this and that's highly accurate, is to simply do delta nRT for the gas species involved in this reaction. Okay, so let's see how in turn this works out for the chemical reaction that we are looking at. Okay, so when we come from this expression and then start to use the data that we have on a per mole basis, that is the following, right? So we'll have the delta RHM, that means per mole, is going to be equal to delta RUM plus this delta nRT of the gas. Okay, that's what we have to do. And here comes kind of the most difficult concepts in this whole problem. The idea is what is constant and what isn't in this parenthesis, and what are the units. Okay, so let's talk about those in turn. All right, so the idea here is that you generally use such small amounts of material or fuel that the temperature actually is not changing dramatically, right? If you think about the amount of, or the change in temperature in the calorimeter, that was just 2 degrees, right? And it turns out that that change in temperature is actually negligible. For all intents and purposes, you can assume that the container is so large compared to the amount of reaction that you're using, that reaction is practically isothermal, right? That is an approximation, but it's an approximation that works really well. And it's useful because if the reaction is considered to be isothermal, then the temperature can be factored out of this change, and then you simply have that this is equal to delta RUM plus RT delta N of the gas. Okay, so again, notice that if the temperature is constant, it can be brought out of this change much as R, which is a constant, can. Right, so really the only thing that you have to do the transformation between enthalpy and internal energy is to figure out what that delta N of the gas is. Okay, and that simply has to do with the amount of moles of gas that you have at the end of the reaction and at the start of the reaction. Right, when we look at the stoichiometry, and this is where balancing the reaction is important, but we recognize that there's only 2 substances that are gases, right? Notice that this is a gas, and that is a gas, but this is not, that is a liquid, and that is a solid, right? Since we have taken here the ideal gas approximation and neglected anything that has to do with the solid and the liquid, then we actually only have to worry about the gas balance between reagents and products. And that gas balance tells you that there's 7 moles in products and only 15 halves in reagents. Okay, so what this delta N gas is going to be is simply, again, the difference between the moles of gas, which is 7, minus 15 halves, which is the moles in reagents. That's it, right? So again, that shows you that balancing that reaction is important. All right, there's an issue with units that I'll discuss as I write the numbers, and that's the last thing that we have to really talk about here. Okay, so now we punch in the numbers, right? The idea is that we know that number, that is minus 32.26 kilojoules per mole. And then we punch in the rest, RT, notice that we have here kilojoules, so I'm going to write here R in kilojoules per mole per Kelvin, so that number is 0.008314 kilojoules per mole per Kelvin. We know the temperature. Here we actually take the temperature to be the initial temperature of the experiment, 298.15, that is 25 Celsius. Okay, but again, this is an approximation, but putting here the final temperature would actually result in a trivial change to the overall enthalpy. So it's an approximation that works actually quite well. And finally, we just have these numbers, that is the balance of products gas minus reagents gas, and we just have to talk about what the units of that are. All right, so notice that the units of this is kilojoules per mole. When you factor in this, or when you cancel out this Kelvin with that Kelvin, you have here kilojoules per mole. So what that means is that what you have to do in the parentheses has to be dimensionless. And it is, right? So what we have here, when we're calculating per mole quantities, this is not the actual number of moles of products minus reagents. Instead, is the per mole quantities of those, which are simply the stoichiometric coefficients. This is simply telling you that if you were to run this with 1 mole, so per mole, you will be generating 7 moles of products, gas, and you would be consuming 15 halves of moles in reagents, right? But because you're dividing this per mole, those units disappear, and these are simply just the balance, or this is simply the balance of the stoichiometric coefficients. Okay, so that's kind of the last sticky point in this whole discussion. Well, you can do all this in your calculator and find that this number is 32.27 kilojoules per mole, which is very, very, very similar to the internal energy, right? So this whole term, that is the difference between enthalpy and internal energy, in this particular reaction only happens to be about 1 gijoule per mole. And again, that tells you that enthalpy and internal energy are generally quite close. Okay? All right, so this has been a long video, but hopefully it has been a useful one, in which we have seen first the basis of adiabatic bomb calorimetry, and then we actually have completed a full analysis of a problem so that you can understand the ins and outs of how to find the enthalpy of a reaction using this technique.